Okay, I'm now going to show how to perform a type derivation. So this is one thing I didn't do during the regular class, but it's actually an important thing to do. So I've shown the rules, but I haven't shown how to plug the rules together. So this is shown a bit in the Hitchhiker's Guide. There are two examples there, and I recommend that you read them, but nonetheless, it often helps to see it in action. So, okay, so I'm going to show how to use these four rules, which we saw in the demo, on a term, to derive an actual judgment. So term, a type, and a context. So I'm just going to close the comment here, open a new comment. I'm going to work here. I'm going to work in my own namespace to avoid problems with other things that are declared upstream. So this is called, let's see, typing derivation. Oops. Yeah, this is how type completion works. Okay, and I'll declare a few symbols. So first, we need some types. I'll call them alpha, beta. Then we'll declare a function f, which is going to be of type alpha to alpha, and a function g that is going to take a function from alpha to alpha and is going to produce something of type beta, right? And now the term I want to check is going to be, let me think, g of lambda x, f of x, right? And you see that Lean is happy with that term, right? That's a good sign. It even types it with beta. It says that the result of all of that is beta. That's not so surprising. That's the return type of g here. So now we're going to try to achieve the same derivation formally to perform formally what Lean did with its check command. And by formally, I mean using the formal derivation system that we have, the four rules here, right? So sometimes formally means, following rules, and sometimes it means following rules in a proof assistant, in a checked manner. So here, I mean the old traditional mathematical meaning of formally. Okay, so we're going to need that symbol, which is a bit hard to type. I'm going to start with an empty context because you see this has no free variables. The only variable is x and it's bound, so we don't need a context. So I could put a context C, but we're not even going to need it. And I want to type that as beta, right? So now what do we have? Which rule should we use? I look at the rules, and here, if we look at the syntax tree of this thing, what we have is not a lambda, it's not a variable, it's not a constant, it's an application. It's an application of g to this lambda expression here. So we're going to use the app rule to do this, all right? So I'm going to draw a big line here. I'm going to write app. And yeah, these things are a bit tedious to write in ASCII art. It goes a bit easier on the board. But even then, it's hard to predict, how wide these trees are. So typing derivations, don't work so well for huge types. Then what I recommend is to introduce abbreviations, say, subtree 1 and subtree 2, and then you can define 1 and 2 in other places. You don't have to adhere strictly to the format that I show here. Okay? So now the application rule, if we instantiate here, right, the T becomes G, the C is the empty list, the U is the lambda expression, the tau is beta. So we instantiate that rule, then we see the two premises we get, all right? And that's actually quite easy. It's going to be the left side with, I'll come back to the type, and the right side of the application, and I'll come back to the type. So let's look at the type. So here we have tau in the conclusion, and here we have something from sigma to tau. So we're going to have something, from I don't know what to B. right? And here we're going to have the same, I don't know what. I could give them names, right? Sometimes you have various I don't know what's, and then you want to keep them apart. But here, suppose that there's, I mean, we have only one variable, so I think 3 question marks will be fine for that. And then we can continue here. We'll say, okay, let's wait. We don't know yet how to fill these question marks. Let's be lazy. Let's continue like this. So we have to type G, and G it's a constant. So it's the const rule, the CST rule that applies. And it says you can type it as whatever you want, as long as it's declared with that type, right? So you have to type it with its declared type. And the declared type is here, right? So we're going to copy paste that because we're lazy, right? And I'm going to glue this all together. By the way, I didn't practice before all of that. So if I make mistakes and so on, well, that's part of the fun of writing a derivation. Or if my lines are too shallow or too short or too long and I need to fix them, I don't know where this is going, but I'm presuming we'll manage. So this is via the CST rule. And then we're done because the CST rule has 0 premise, right? And the best way to indicate this is to just put a bar like this. That says that branch is closed. Some people don't do it, some people do it, some people use other symbols, like they would put a dot on it. I think this is the clearest because it's saying, well, you know, at this point, we don't need to do anything. Actually, I told you that I would be doing things wrong, and I just did things wrong because what I really wanted to do with my copy paste was to plug in this type in here. And then we apply the CST rule and there is no premise. This is what it should have looked like. So I was just trying to confuse you there and I was confusing myself. We started with that rule. Then we didn't know what to put here. We applied the const rule. The const rule has 0 premise. So we see them, you know, all 0 premises are here. And here we see now that we apply the const rule, we know what goes here, right? This is how it should have been, okay? Now, now we continue with the right-hand side and we'll try to get it right first time around this time. Because I don't want to make so many mistakes that I have to restart the whole video, okay? So which rule applies? Well, we have a lambda expression, right? So lambda expression here, it's called lam, the rule. And what happens is that the x of the lambda moves to the context, right? So all of a sudden we're going to have x. Okay, what is the type of x? Well, it can be inferred from the context, right? So here, if I go with the cursor, it tells me it's alpha. So I can already put alpha if I want, or I could have put, whoops, alpha is just backslash a, or I could have put other question marks and wait to see what happens. Okay, but typically for bound variables, we can just cheat. We can just yeah, look at the term. Or guess it ourselves. So then we have the body, which is f of x, and this is going to have type, let's see. So the lambda rule, the conclusion has to be a function, has to be sigma to theta. And what we know is that it's a question mark, right? So I'm going to refine that. It's like, oh, now we have more information. A lambda must be a function, right? So I could say question mark to question mark, but that's just too confusing. We don't know which is which. So I'm going to switch to using Greek letters for these unknowns, but I'll put question marks in front just to clarify, right? So we're getting more and more information. This is what's happening. We're gaining more and more information about the types that we don't know at the bottom. And we're lazily, you know, filling in that information as we apply rules. So now f of x has, you see, has to have type tau, right? We don't know yet what that is. And then we'll continue. So what do we have here? We have f of x. F of x is an application. Right, so we're going to have two branches again. We're going to have to type f, and we're going to have to type x. So I'm going to do the two branches. So here we have to type f, all right? And because it's an application and the app rule is of the form sigma to theta, it's going to be something or other goes to theta. Right? So it's very mechanical, but yet it's very easy to make mistakes, right? So my proposal is to maybe adopt clear conventions from the beginning, say, always use Greek letters, or maybe instantiate those rules explicitly, right? If you need an app, you can replace all the t's, all the taus, etc. by your conclusion, then you see exactly what you have as your premise. Whereas now I'm trying to do that mentally. And mostly succeeding, but not always. But what I mean is it's a very mechanical process, and with enough discipline, you can carry it out. Okay, and it's good practice. And then you have the other side here. Tack. So now we have to type the x. And now, well, I'm going to cheat. I'm already going to go here because it says in the context where x has type alpha, I can type x as what? So I already know that my tau is going to be alpha. And that will trigger a whole sequence of simplifications here, right? And that branch is now closed because what I have is a variable. And this is the var rule. This is exactly the var rule, right? So if x sigma occurs in C, then x sigma is a valid type, and this is exactly what we have. Now we continue on this side. We're going to need to do something here. Well, f is a constant, so this is going to be the CST rule. There are only 4 rules. It's quite repetitive. It's a bit boring, right? And then the question is, what is the type of f? And it's alpha to alpha, right? So here, these 3 question marks are actually just alpha. And that, now what I'm seeing is a complete tree. You see every branch is closed. So this branch is closed, this branch is closed, and this branch is closed. And CST and var have no premises. Well, basically these are the 2 rules that have no premises. So these will always be the leaves of the tree. An app will create 2 children, a lamb will create 1 child, 1 premise when you go bottom up, right? So you see, I've really built the tree bottom up. I started with a goal. I wanted to show that certain term has a certain type, and then, I went up. It would be very hard to build these things in the other direction because this will not be goal directed. You have to start by guessing, oh, I should use cons for this, or I should use var for that. And why would you do that? You'd have to know in some sense where you're going. It's easier to go backwards and to tear this term apart as you just shut this up. Okay, now I would like to do a second example, which is almost the same, and this will just take a minute. I'll replace the f by the g by an f, right? And then we see that we have an error, right? And now let's try to see what happens when you start with an ill-typed term. Can you find a typing derivation? I hope not. So we start with the f here. We have the application. Right? The application is going to say, well, we don't know what the argument is, right? But we'll come back to that later. And oh, here I see a sigma. The sigma I should have filled out earlier. This is just a leftover, but it should have been an alpha. There were some constraints, a constraint which I missed, which mean exactly that. Sorry about that. Actually, let's just undo. and do it properly. Right, so we had finished the proof here, right? And then we had the sigma left, and we're like, what? I mean, we shouldn't leave these variables. They help us while we, oh wait, that wasn't quite finished. Yeah, there. So here, we shouldn't leave these variables around. This is not a typing derivation. This is just, you know, it's a placeholder for a type, but the typing derivation requires an actual type. So where does the sigma come from? How can we type this properly? Well, I think what happened is when we applied the lam rule, we, we at some point we said, oh, we know what's the type of X, it's alpha, and then we plugged it here. But actually what we should have done properly is just propagate the sigma here, propagate the sigma there, propagate the sigmas, and then eventually discover that the sigma is alpha. We should not have maybe cheated using the term, or if we wanted to cheat, then we should have we should have put the alpha right away, right? You know, there's nothing wrong with making a guess, you know, like, so if I start from here, there's question marks. If I guess, oh, this type I think will be this, or this type will be that, you're completely allowed to make the guess. It's just that if you cannot finish the tree, then that means nothing. It doesn't mean the term is not typable. It might just mean that you've made the wrong guess. But it's completely all right. It's fully in ordnung to make guesses when you're you know, doing a type derivation, or later when you're going to write proofs. You know, that's what proving is all about. Okay, so now we resume the experiment with the you know, with the F instead of the G. Right, there it is. I forgot to remove it. And then, you know, I went upstream here, and then, well, we don't know what this type is going to be. I mean, all of this is garbage for the moment. We haven't updated it, right? And then this part here is just like before, right? This term hasn't changed. The only thing we've done is replace the G here by an F, right? So it's this branch that changes. But now we see the problem. The problem is that we cannot apply the const rule, because the const rule would require F to have type alpha to alpha, and we need something of type question mark to beta. So we cannot apply the const rule. This doesn't work. And therefore, I mean, the rest of the proof is fine, the derivation tree, but this branch here we cannot close. And there's just no way to close it, because the beta will never match alpha, and that's the end of it. Okay, well, I hope this derivation was instructive. I hope you've learned from the things that I've done wrong, just as much as you will have learned from the things that I've done right. So there will be, I think, such a derivation in the homework. It's the last exercise. It's quite difficult. If you don't manage it, it's not the end of the world. You know, I don't think everybody should always have 10 points out of points at all homeworks, but I think it's a good challenge.